So, we have discussed about the Pelton wheel, which is an impulse turbine, and we have discussed about the net head available on the wheel. So, the net head available on the wheel is H gross minus Z minus HL. So, if I go back to my previous slide where it is clearly seen that the net head available is, of course, the total gross head is basically the head available between the HRL and TRL, that is head rest level and tail rest level, but the net head available on the wheel is H gross minus this height Z and the frictional losses that is there when liquid fluid is flowing through the penstock. So, this is the net head available in the wheel. Now, we need to quantify, okay fine, that is what we have discussed, that maybe power whenever now fluid is flowing through the nozzle, I mean then the head is, we are getting some kinetic energy of, we are getting velocity, so kinetic energy. So, the power output from the nozzle may not be the power transferred by the fluid to the wheel. So, there will be a certain amount of losses and we need to know what are the losses, and before we going to discuss about the losses, let us first try to analyze what is the efficiency, and to do that we need to draw the velocity triangles at the inlet and outlet. So, today we will now draw the velocity triangles at the inlet and outlet whenever fluid is flowing through the penstock and it is going to the nozzle, and ultimately the jet is striking the buckets of a Pelton wheel. So, if I draw the velocity triangles, and probably we have discussed about the bucket shape, we have discussed about the function of different parts of the bucket like a splitter, reach and notch, and bucket is so designed that we also have discussed that if the deflection of the jet is exactly opposite to the incoming jet, then we may have probably higher efficiency, but this is not the case, because in that case the outcoming jet from the bucket might create resistance to the jet which is going to come, and in that case it will create resistance for the wheel rotation. So, we will now draw the velocity triangles at the inlet and outlet, and to do that, suppose we will now quantify the wheel efficiency or efficiency of the Pelton wheel. So, today we will discuss about wheel efficiency of a Pelton wheel. Wheel efficiency of Pelton wheel of Pelton turbine. So, we need to draw the velocity triangles at the inlet and outlet. So, you know the bucket shape. So, suppose liquid is coming from the nozzle, liquid from reservoir, it is coming through the penstock, then it is taken to the nozzle. So, this is penstock. So, this is from penstock, then this is nozzle, and then the jet is striking the buckets. So, whenever jet is striking the bucket, as I said you, there is a splitter ridge, so which divides equally the incoming jet into two parts, and then the jet follows the round shape of the round inner surface of the bucket and coming out from the bucket. So, the jet which will going and ultimately it will come out. So, suppose so now jet will come out like this, following the so this is the bucket. So, this is the bucket, and jet is after striking the bucket, it follows the round inner surface of the bucket and coming out from the bucket. That is what we have discussed last day. So, now we need to draw the velocity triangles. So, the fluid which is coming out from the nozzle, so maybe if I extended this portion, then this angle, let us say this is theta, this angle is theta, and this is the velocity of, this is the relative velocity, I mean this is the relative velocity at the outlet. So if I draw and the velocity of the jet which is coming out from the nozzle, that is CV, that equal to so absolute velocity of the fluid coming out from nozzle, C1 is equal to CV root 2G into H. So G is the head available. Now the inlet velocity triangle, that is very important, inlet velocity triangle, that we need to know. So inlet velocity triangle is like this. So this will be W1 and this is U1 and this is W1 and C1 is total. So this is the C1 is equal to C theta 1. So this is the inlet velocity triangle. So this is inlet velocity triangle, and we can have outlet velocity triangles, that we know that this angle is theta. So and this will be our absolute velocity, this is W2, this is C2 and this component will be C theta 2, and this will be equal to U2. Here U2 is equal to U1, so is equal to pi d and 60. Here U2 is equal to U1 is equal to U is equal to bucket speed is equal to pi dn by 60, where d is the pitch circle diameter, right. So pi dn by 60, that will be blade speed, bucket speed, pi dn by 60, d is equal to pitch circle diameter. We have drawn the inlet velocity triangle, and this is the outlet velocity triangle. Sorry, this is outlet velocity triangle. So now from the inlet and outlet velocity triangle, we can now quantify what should be the change of momentum. So from there we can estimate about the wheel efficiency. So note that we can write that from the inlet velocity triangle, that C theta is equal to Vu, that is basically flow velocity. Now so what is the change in absolute C theta 2 and C theta 1. So C theta 1 minus C theta 2, that is what is very important, that is the change of swirl velocity between the inlet and outlet of the bucket, change in swirl velocity between the inlet and outlet of the bucket. So that I can write C theta 1 and so this is inlet velocity triangle and this is outlet velocity triangle. So C theta 1 from the inlet velocity triangle I can write that it is equal to C1, and C theta 2 I can write from the outlet velocity triangle. How? So C theta 2 is equal to U minus W theta 2. So what is W theta 2? W theta 2, so this is W theta 2. So C1 minus U minus W theta 2. So that is the change in swirl velocity. So what is C1 minus U, what will be W theta 2, because this angle is theta, so this will be minus W2 cos 180 minus theta. So this is cos 180 minus theta. So what is C1? So from inlet velocity triangle we write, from inlet velocity triangle, what we can write, C1 is equal to U plus W1. So if I put the value of C1 here, so that is U plus W1 minus U plus W2 cos theta. So this is the component that we are getting. So if I go to the next slide, then I can write change of swirl velocity as fluid is striking the jet from after coming out from the nozzle. So change in swirl velocity, that is again I am writing change in swirl velocity C theta 1 minus C theta 2, that is equal to U plus W1 minus U plus W2 cos theta. So how we can write? So W1 into 1 minus W2 by W1 cos theta. So this is the change in change in swirl velocity as the fluid is coming out from the nozzle and striking the jet. That is what we obtain from the inlet and outlet velocity triangle. Fine. This W by W2, that is the relative speed ratio of relative velocities at outlet and inlet. If I write in terms of K, which depends upon the roughness of the blade. So this K, which depends upon the smoothness of the blade surface of the blade. So it depends upon the smoothness of the blade. So if I write, that is W1 into 1 minus K cos theta. So K is the ratio of relative velocities at the outlet and inlet, which depends upon the blade smoothness or roughness of the blade. So now we can define blade efficiency or wheel efficiency. Wheel efficiency eta wheel, that is can be defined as the ratio of power transferred by the fluid to the wheel, transferred by the fluid to the wheel, to the what? Power input to the wheel, power input to the wheel, which is obtained from the nozzle output, from the kinetic energy of the jet arriving at the wheel, which is obtained from the kinetic energy of the jet, that is power input to the wheel, that is power output from the nozzle. So kinetic energy of the jet arriving at the wheel. So these two ratios, so wheel efficiency, which is defined as the ratio of power transferred by the fluid to the wheel, of course very important, to the power input to the wheel, that is why I said that power input to the wheel, that is the kinetic energy which is coming out, the kinetic energy leaving the nozzle may not be transferred to the wheel shaft. So there will be some amount of losses. So the ratio between these two, power I mean we can call it a wheel efficiency. So wheel efficiency is defined as the power transferred by the fluid to the wheel to the ratio to the power input to the wheel, that is which is obtained from the kinetic energy of the jet arriving at the wheel. So now what is power transferred by the fluid to the wheel? That is rate of change of momentum. That is what you can write, that rho into q into u into c theta 1 minus c theta 2, c theta 1 minus c theta 2, that is change of momentum, no, because fluid is taking a direction, there is change in direction of the fluid, so there will be rate of change of momentum. So the change of momentum is basically rho q u into c theta 1 minus c theta 2 divided by what is the power output to the input to the wheel. So that is the kinetic energy which is obtained from the kinetic energy of the jet arriving at the wheel, that is half of course into rho into q into c1 square. So now I can write this will be equal to twice u into c theta 1 minus c theta 2 divided by c1 square. That is what we obtain. Now we can rearrange this term in a bit different form, what I can write. So if I go to the next slide, then the expression of wheel efficiency eta wheel, that is what we obtain is twice into u into c theta 1 minus c theta 2 divided by c1 square. So I am rearranging this term, that is twice into u by c1 into c theta 2 minus c theta 1, that is what we obtain from the inlet and outlet velocity triangle is or I can write that is twice w1 by c1, because w c theta 1 minus c theta 2 divided by c1, that is c1. Now c theta 1 minus c theta 2, that is equal to, we have obtained w1 into 1 minus k cos theta. So this expression will be twice u by c1 into w1 by c1 into 1 minus k cos theta. Note that w1 from inlet velocity triangle is equal to c1 minus u1, right. That is what we can obtain from the inlet velocity triangle. w1 is equal to c1 minus u1, that is c1 minus, that is c1 minus u. So that is twice u by c1 into w1 is equal to c minus u1, so there is 1 minus u by c1 into 1 minus k cos theta. So this is the wheel efficiency eta w. So eta w is equal to twice u by c1 into 1 minus u by c1 into 1 minus k cos theta. So this is known as wheel efficiency. There, I mean, this is the expression, mathematical expression for the wheel efficiency. Now for maximizing, so our target will be to obtain maximum wheel efficiency. That is what I discussed, that if the jet deflection, deflection of the jet by suitably designing the bucket can be done, that it should deflect exactly in the opposite direction. It is coming out almost in the opposite direction, not exactly the opposite direction, but if it comes exactly in the opposite direction of the incoming jet, probably then we may get higher wheel speed, but that will create another problem, that may strikes to the preceding jet which is going to come is continuously rotating, and instead of having higher wheel speed, it may create resistance to the wheel rotation. So we may have a drop in the efficiency. So that is why theta, that is deflection angle, is 165, that is the maximum deflection that can be done to obtain the maximum wheel efficiency. That can be obtained from this expression also. Now what we can write, that for maximum wheel efficiency, what we can do, so that d u by c1 is very important. So u by c1, this ratio is known as speed ratio. This is known as speed ratio. So velocity of the blade to the absolute velocity of the jet, right, or fluid striking the blade, that is speed ratio. Now what we can obtain for maximizing, for maximum wheel efficiency, for maximum wheel efficiency, what we can obtain, d eta w divided by d by u by C1, that will be equal to 0. So, if we do this, then what I will get? It is very easy. That means, if we make it d eta w by d by u C1 is equal to 0, from this we get C1 is equal to twice U1. So, I mean, I will tell that if we make it, we get C1 is equal to twice U. That means, U by C1 is equal to half. U by C1 is equal to half. So, if U by C1 is equal to half, that is speed ratio is equal to half. So, speed ratio will be equal to half. So, this is the for maximum wheel efficiency we get it, d eta w by d u by C1 is equal to 0, and we obtain u by C1 is equal to half, that is speed ratio is equal to half, and then the eta w maximum will be equal to how much? If u by C1 is equal to half, then it will be equal to half into 1 minus k cos theta. So, this is the maximum wheel efficiency that you obtain. So, and that is obtained for a speed ratio is equal to half. So, this is what is very important. So, we need to know that speed ratio is equal to half, we can have obtain higher wheel efficiency, but it is seen that it is very important that it is seen that we have seen that the energy transferred from the fluid to the bucket is not, energy transferred from the fluid to the bucket is not completely transferred to the output shaft, very important. So, if I go to the next slide, so from the last slide we have seen that if speed ratio, that is u by C1 is equal to half, then we have higher wheel efficiency, that is half into 1 minus k cos theta. Now, my question is, my point is, the energy transferred from the fluid to the bucket is not wholly, rather totally transferred to the output shaft of the machine. So, I am writing the energy transferred from the fluid to the bucket is not totally available to the output shaft of the machine, to the output shaft of the machine. This is very important. So, energy transferred from the fluid to the bucket is not totally available to the output shaft of the machine, because there are losses. Some energy is converted to, because this is very important, because a portion or of some energies, a portion of the energy, a portion of available energy is used to overcome the bearing friction and windage loss. So, this is very important. That means, a portion of available energy is used to overcome the bearing friction, because all the machines are connected in a common shaft. So, there will be a, we have to overcome the frictional losses will be there. Not only that, windage loss. What is windage loss? That resistance created by the air, because when wheel is rotating along with the buckets, so there will be some amount of frictional resistance offered by the air, and that is windage loss. So, and also nozzle is also an integral part of the this Pelton turbine. So, losses in the nozzle also contribute that the reduction of overall efficiency of the machine. So, what I am telling, nozzle is also integral part of the Pelton wheel. So, there will be losses in the nozzle as well. So, the losses in the nozzle also reduces the overall efficiency of the machine. So, what we have seen that if I now try to draw the efficiency versus speed ratio U by C1 and this is efficiency, and it is seen that eta when maximum speed ratio maximum efficiency is obtained when U by C1 is equal to 0.5. So, this is U by C1 is equal to 0.5. So, that is eta max. So, this is known as eta max. Eta max. I am writing theoretical. So, this is eta max theoretical. So, this is an theoretical one. So, what I am said that energy transferred from the fluid to the bucket is not totally available to the output set of the machine, because a portion of the available energy is used to overcome the bearing friction losses as well as the windage losses, because when Pelton wheel is running, then of course because it is not totally covered by the fluid like a reaction turbine. So, the air will create resistance to the rotation of the Pelton wheel, that is why there will be some amount of losses, that is known as windage loss. Not only that, since nozzle is also an integral part of the Pelton wheel, so we need to take into account the losses in the nozzle itself, and the losses in the nozzle itself also will try to reduce the efficiency of the Pelton wheel. So, accounting all these losses, even if although we have derived that the maximum theoretical efficiency is obtained for a speed ratio is equal to 0.5, but if we take into account all these losses, it is seen that the actual efficiency, actual maximum efficiency which is obtained slightly less than the speed ratio, and which is 0.46. So, actual curve, actual efficiency, actual maximum, actual case is always less than So, this is U by C1 is equal to 0.46. So, this is actual curve. So, the theoretical value 0.5, that is we have obtained from maximum wheel efficiency, that is a theoretical value, but because of the losses that is what we have discussed, and that bearing friction losses, windage losses and losses in the nozzle itself, we will reduce the value of speed ratio to 0.46, I mean at which the maximum wheel efficiency is obtained. So, this is what is all about the wheel speed and wheel efficiency, and we will discuss about the pump specific, turbine specific speed, and also the similarity law, and we have discussed about the Buckingham pi theorem when we have discussed about the pump, and from that theorem we have derived a few coefficients, that is head coefficient, flow coefficient, also the power coefficient. So, all these three coefficients are also remaining also true for the hydraulic turbine as well. Only the difference is in a pump the direction of energy conversion is different than what is happening in the turbine. So, now we will proceed to solve a numerical problem. So, this is all about the Pelton wheel, that we have seen. The Pelton wheel is very important, that Pelton wheel is only the hydraulic turbine of impulse type which is commonly used. So, I am writing that Pelton wheel is only the hydraulic turbine of impulse type which is commonly used, and it is particularly suited for high heads, and sometimes Pelton wheel is called as tangential flow turbine. Why tangential flow turbine? Because we have seen that the jet is striking almost in the tangential direction of the pitch cycle diameter. So, just like a reaction turbine we have classified a radial flow, axial flow, sometimes it is known as tangential flow turbine, and it is on Pelton is only the hydraulic turbine of impulse type which is commonly used, and it is in general suited for high heads. I also would like to discuss in this context that we have seen this turbine is, I mean, will produce power. Suppose I would like to generate a certain amount of power using a hydel power plant, where maybe in one case we have impulse turbine, let us say Pelton wheel, in another case we have a Francis turbine, that is reaction turbine. Since Pelton wheel is normally suited for high heads, so to obtain higher output we require high heads, but sometimes it is not possible to have high head. Then what we have to do, only we can increase the if we would like to get suppose more amount of power from the same Pelton wheel, then we need to increase the wheel diameter. So that will increase, or we have to have more than nozzles. So for that we have to have higher bigger size of the turbine, and that is not, and that is why to obtain the same power it is always recommended that a reaction turbine will be it is always recommended to have a reaction turbine. Anyway, so with this now we will proceed to solve a numerical problem, from where it will be clear that how we can obtain efficiency from the given values of head and other, I mean, nozzle diameter and all those things. So we have discussed that Pelton wheel is normally suited for high heads. So if you would like to obtain same power from the Pelton wheel, then of course and reaction turbine, for the given power output Pelton wheel requires a high head, or if we do not have high head, then we have to have a few more nozzles, and also the wheel diameter has to be increased, and that is not recommended, because in that case it will increase a bigger size. So in that case, I mean, reaction turbine is very important, because reaction turbine can be operated even at a moderate head to obtain the same power output. So now we will solve one numerical problem related to this impulse turbine. So let me write the problem first, then we will proceed to solve. So problem is, in a hydraulic electric scheme a number of Pelton wheels are, so a problem in a hydro electric scheme a number of Pelton wheels are to be used under the following condition. Right, total output power required is equal to 30 megawatt, gross head is equal to 245 meter, speed is equal to 39.27 radian per second, that is 6.25 revolution per second. It is given 2 jets per wheel. CV of the nozzle is equal to 0.97, that is coefficient of velocity. Maximum overall efficiency based on the condition immediately before the nozzles, maximum overall efficiency is equal to 81.5%, that is given, that is based on the condition immediately before the nozzle, based on the condition immediately before the nozzle, and power specific speed for one jet not to exceed power specific speed, this is important, power specific speed for one jet not to exceed 0.138 radian, that is 0.022 revolution. Head loss to friction in pipeline not to exceed 12 meter. Head loss, head loss due to friction in pipeline not to exceed 12 meter. So, what we have to calculate? First we have to calculate number 1 is the number of wheels required, the number of wheels required, 2 diameter of the jets and wheels, diameter of the jets and wheel, 3 hydraulic efficiency, if blades deflect water through 165, if blades deflects water through 165 degree, this is very important, and reduce the relative velocity by 15%, and reduce its relative velocity by 15%, and 4 percentage of the input power that remains as kinetic energy of water as discharge, percentage of input power that remains as kinetic energy of water at discharge. So, we have to solve this problem. So, it is given that in a hydraulic power plant scheme Pelton wheels are to be used for the following conditions. So, we need to develop or generate 30 megawatt power, gross head is available 245 meter, speed is given 6.25 revolution per second, and there are 2 jets per wheel. Nozzle CV is given 0.97 coefficient of velocity, maximum overall efficiency 1.5% based on the condition immediately before the nozzle. Power specific speed for one jet not to exceed 0.022 revolution. So, we have to calculate head loss due to friction in the pipeline. If head loss due to friction in the pipeline not exceeds 12 meter, then the number of wheel records, diameter of the jet and wheel, hydraulic efficiency if blades deflects water through 165 degree and reduce the relative velocity of 15%, and percentage of input power that remains kinetic energy of the water at the discharge. So, we have to solve this problem. So, the solution, this is very important, we have to solve the problem that, so what is given? So, total power, it is given total power required P naught is equal to 30 megawatt, that is given, and Ns is equal to given 0.022 revolution per second, that is given, because this is given power specific speed for one nozzle not to exceed it, and H gross is equal to 245 meter, frictional losses will not exceed 12 meter, that is given, speed is given 6.25 revolution per second or RPS revolution per second, Ni is equal to 2, that is number of that is given, that 2 jets per wheel, that is given, CV is equal to given 0.97, and efficiency is equal to given 81.5%. So, based on that we have to calculate. So, we know that we will drive specific speed of the turbine, that is equal to n root P divided by rho to the power half root GH effective to the power fifth, that is to the power 5 by 4. So, H gross is given. So, H effective is equal to H gross minus HL, that equal to 245 minus 12, that will be 233 meter, that is given, right. And P naught total power is equal to NW into Nj, number of jets per wheel, N jets, number of jets per wheel, Nj is equal to 2 into P. So P will get from that expression of specific speed, if we calculate. So P will get from this expression P, because Ns is equal to given, so we will calculate P, and that will coming out 3.095 mega W per jet, because you have this is valid for a per jet. So if I calculate P, this one, and from this expression if we know P naught because 3 megawatt, so 30 megawatt, and this is given 3.095 into twice into NW. Therefore, NW number of wheels will be equal to 4.85, this is almost equal to 5, that is number of wheels. So from the expression of power specific speed, that is given 0.022 revolution per second, that is n root P by rho to the power half G H effective to the power by 4, because H effective is H gross minus frictional loss, that should not exceed 12 meter. From there we calculate P, that is the power, that power into number of jets per wheel multiplied by the number of wheels will be the total overall power, that is total power required. From there we have calculated the number of wheels should be 5, it should not exceed 5. So there are, since there are 2 jets per wheel, so there are, this Nj is equal to twice jets per wheel, fine. So next we have to calculate other solution, that is what is other we need to calculate, that is diameter of the jets and wheels, that you have to calculate. Okay, then you have to calculate. So from inlet velocity triangle, we know C1 is equal to CV root 2G H, this H should be H effective, right. So we can calculate the absolute velocity of water leaving the nozzle, that is equal to will be 0.97 into root 2 into 9.81 into twice 33, 233, that is equal to 65.58 meters per second. So this is the absolute velocity. Now we have obtained from the curve that U by C1 is equal to 0.46 for maximum wheel speed. So if I know C1, then I can get 0.46 multiplied by C1, that will be equal to 31.17 meter per second. So this is optimum speed ratio used in Pelton wheel, optimum speed ratio used in Pelton wheel. So this is 30.17 meter per second. So now question is, U is equal to the blade speed or bucket speed, that is equal to pi dn by 60. So 30.17 is equal to pi and d into n is equal to, that is given, n is equal to, I know that RPM is equal to given 6.25 revolution per second, 6.25 divided by 60. From there we can calculate d is equal to pitch cycle diameter, that is equal to 1.536 meter, because that is what we need to calculate, that diameter of the wheel. So this is 1.56 meter. Then what we have to calculate, that nozzle diameter of the jet is very important. What is diameter of the jet? Now we know that P naught is equal to rho G Q naught into H effective into eta naught overall efficiency. So Q naught will be equal to 30 into 10 power 6 from this expression, 30 megawatt, where rho I know 9810 into twice 33 is H effective, and overall efficiency is given 0.81.5%, that is 0.815. So from there we can calculate what will be the flow rate, the discharge, that is equal to 16.104 meter cube per second. So now discharge per jet, if you would like to obtain this amount of power, then it should be the total discharge. So discharge per jet will be Q naught divided by N W into N J. So now discharge per jet will be equal to how much? Pi by 4 into nozzle diameter square into C1, that will be equal to Q naught divided by N W into N J. So this is N W. So if I calculate this, and that is, so pi by 4 d square into C1, that will be equal to how much, you know, Q naught divided by Nw into Nj. So from there we can calculate that C1 is equal to, you know, 65.58 meter per second. That is what we have obtained, you know, that is what we have obtained CV value of absolute velocity. Then we know Q naught, and that is 16.104 divided by number of wheel 5, number of jet 2. From there we can calculate jet diameter D will be equal to 0.177 meter, that is 177 millimeter. So 70 of the centimeter. So K is equal to given that 15% loss. So that means, sorry, so K is equal to 0.85, K is equal to, that is W2 by W1, that is 0.85, I mean given, because 15% loss, that is given. So eta hydraulic will be equal to UW1 into 1 minus K cos theta, theta is equal to given, theta is equal to 165 degree divided by G into 1 by H effective. So, and if I calculate it, U into C1 minus U into 1 minus K cos theta divided by G into H effective. So I know everything, U I know C1, I know K I cos theta, K is 0.85 because 15% loss of the 15% of the reduction of the relative velocity. Then we can calculate what would be the value of hydraulic efficiency, and that will come around 85.1%. So this is the hydraulic efficiency of the turbine. So this is the way we have to solve the, if we know the power output, that is what we need from the Pelton turbine, and then we have to calculate what should be the hydraulic pitch cycle diameter of the wheels, what should be the diameter of the jet, and number of wheels is required. One important thing is that because the gross head is not equal to the net head available at the wheel. So we need to calculate net head available at the wheel, and based on that we can calculate what should be the, other parameter, that is diameter, efficiency, and also the hydraulic efficiency. Hydraulic efficiency, that is what we have defined here, UW1 into 1 minus cos theta by G by H effective, because UW1 into 1 minus cos theta by G, H effective is the effective head available, but out of this effective head how much amount of, we are getting the, that is power transferred to the fluid, that is important. So although we are having H effective is something else, but that head is not be converted to equivalent amount of kinetic energy or the energy of the rotation of the wheel. So, and since from there we can calculate what will be the hydraulic efficiency. So with this I stop here today, and we will continue our next discussion in the next lecture. Thank you.